I'm John Falcione, the editor of ASME's flagship publication, Mechanical Engineering Magazine, and I'm the host of today's webinar, which is being brought to us by Simulia, a part of the Dassault Systems company. Simulia is a leading provider of realistic simulation solutions, including the Abacus product suite for unified finite element analysis and multiphysics. For those of you who may be unfamiliar with Simulia, it is used to create realistic simulations that help produce physical prototypes and improve product performance. Today's webinar is another chapter in our continual series of events that bring you state-of-the-art solutions to some of the real-world engineering challenges of the day. In today's program, we focus on composite optimization, emphasizing reliability and robustness. This webinar is aimed at exploring the latest methods for applying simulation processes. As you're well aware, designers today use computer-aided product development and manufacturing software tools to design and simulate products they're creating. The computer-aided product development and manufacturing environment has prompted designers and engineers to use a wide range of software tools. This often results in the need to transfer data manually from one software package to another. The problem is that this manual process reduces efficiency. It slows product development, and it introduces errors in modeling and simulation assumptions. To make matters worse, most design optimization tools can't concurrently optimize structural strength, failure modes, manufacturability, robustness, and reliability. Our speaker today, Kyle Indermuhle, will talk about the latest technology methods used to apply simulation process automation and design optimization to improve the efficiency and the effectiveness of the product development process. This webinar will also include a discussion optimizing a composite winglet, focusing on strength and composite failure, as well as the full process for automating the evaluation and creation of robust and reliable designs. The takeaways for today's program are, first, for you to have a good grasp on how to set up simulation process automation using EyeSight from Simulia. As you'll hear from our speaker, EyeSight is a solution that gives engineers a suite of visual and flexible tools for creating simulation process flows. Second, our hope is that you'll better understand how to be able to account for variations in material properties and manufacturing with more accuracy. And thirdly, we hope that you will better understand how to perform rapid, reliable, and robust optimization studies. It's now time to introduce our speaker, Kyle Indermuhle. Kyle works in the technical marketing group at Simulia and focuses on the aerospace industry. Before joining Simulia, Kyle worked on a variety of aerospace programs, including the Pratt & Whitney RL-10B-2 rocket engine. He also analyzed and tested unmanned aerial vehicles and satellite programs. Kyle received his Bachelor's of Science in Aerospace Engineering from Purdue University and earned his Master's of Science degree in Structural Engineering from the University of California, San Diego. Finally, I'd like to thank Simulia for being the sponsor of today's webinar. Our speaker has an interesting presentation to make. I know that because I've seen the slides earlier. So without any further ado, I'd like to call on Kyle to get our program underway. Kyle?
Great. Thank you, John, and thank you, everyone, for attending the webinar today. As you know, the title of the webinar is Composites Optimization with Focus on Reliability and Robustness. So John introduced me, so thank you for that, John. I'm going to introduce Simulia just a little bit. Simulia, the company I work for, is part of the Dassault Systems family of brands, which includes CATIA, Simulia, Delmia, Innovia, 3Dvia, and SolidWorks. Our brand, Simulia, is responsible for realistic simulation. So what is realistic simulation? Realistic simulation is the use of finite element analysis and multiphysics simulation to know how products will perform before they are built. It allows you to evaluate design alternatives, reduce the number of physical prototypes, increase the confidence in product performance, accelerate design decisions, and gain knowledge of real-world behavior. Simulia solutions fall under a number of different categories. We have solutions for unified FEA. which includes scalable solutions with the Abacus solver. We also have simulation products that reside and are integrated with CATIA, SolidWorks, and other CAD products. We also have solutions that focus on multiphysics and design exploration and optimization, which is going to be the topic of today's presentation. And we also have solutions for simulation lifecycle management. Simulation lifecycle management is a collaborative environment to manage simulation processes, data, and intellectual property. Our actual product portfolio includes Abacus, Unified FEA, Multiphysics, iSight, which we're going to talk about today, SLM, CATIA V5 Design Analysis, and the just released CATIA V6 environment, which includes Simulia simulation products, including DesignSight and Xsight. If you want more information on any of these products, feel free to visit our website or feel free to contact me after this presentation. Today I'm going to focus mostly on iSight. This is our product for design, optimization, process automation, and also methodology standardization. So with that overview of Simulia and our products, let's get right into what we're going to focus on today. So the presentation today is really going to look at the optimization of a composite winglet. So this is an example problem that we chose. We're going to apply some loads to this winglet, and we're really going to try to understand how we want to do the composite layups and what is the best optimized design. So if we're going to optimize a design and perform an optimization, we really have to understand what is the real goal of optimization. So I've asked this question to a lot of engineers and people over the years, and most people will first say, well, the goal of optimization is to lower the weight of a part or lower the weight of a particular component. And that's true, but that's only one small aspect. That's not the real goal of the optimization. You also want the part that is manufacturable, right? Other people say that the goal of optimization is to be just strong enough to survive the applied loads, have a margin of safety of 0.0001. So the absolute minimum amount of product that will withstand that load case. And again, that's true, but it's just another aspect. It's not the real goal of developing and producing a product. What about reliability? What about the lifespan of this part or this product? Other people will say that the real goal of optimization is to reduce the cost of a part or a component. And that's getting a little bit closer, but what do you mean by cost? Does cost equal weight? Does this include manufacturing costs? What about repair and replacement costs for 20 years of life of this product? So what we're going to do is really kind of look at this real goal of optimization. We're going to look at some of the traditional goals, including we want it to be lightweight, we want it to be strong enough to survive the loads, but we're also going to think kind of beyond our cubicle. You know, most of us engineers sit in one cubicle and think about one part. But we're going to go beyond our cubicle and think about easy assembly to the rest of the wing, thinking about manufacturing. Reliability, having no in-service failures, thinking about the operators, the cost of repairs. Having a consistent performance between the hundreds of products that are produced, thinking about the customers and the passengers. And we also want it to be cheap to build, easy to manufacture, no exotic materials or processes. So we're thinking about the company's expenses as well. So the real goal of optimization is to design a part or a component or a vehicle that performs its task with high performance, low cost, and is reliable and robust. So let me talk a little bit more about reliability and robustness and give an example of exactly what I mean by that. So in this graph, you can see we're going to start our design process, and we may have an initial design that we do. Maybe it's from a design of experiments. We're then going to go through a traditional optimization. And this traditional optimization will kind of speed us along some path and get our design to essentially exactly on this constraint boundary that we have. Maybe a peak stress, maybe a critical fracture criteria that we have. But this traditional optimized design will put us right on that critical edge, right on that boundary. But what if we start to think about variabilities in manufacturing, variability in material properties? When we include those variabilities, what we'll see is that we have a certain percentage of our product that's going to be built that's going to be reliable. It's going to fall inside of this constraint boundary. And we're also going to have a certain percentage that is unreliable. It's going to fall outside of that constraint boundary. There's always variability in the real world. So what we're going to do is perform an optimization where we can actually optimize, including that variability, and come up with a design that's just inside of that constraint boundary, so all of our products as produced, including all the variability, is reliable. So to perform this task, we're going to use EyeSight. EyeSight is primarily a toolkit for process automation. It allows us to string together a number of procedures, pre-processing, solving, post-processing, calculation of different failure criteria, margins calculations. EyeSight also includes a very powerful suite of exploration tools. This includes optimization, design for Six Sigma, design of experiments, Monte Carlo, and reliability and robustness. EyeSight is not a new product. It was actually acquired a couple years back by Simulia. It was acquired from a previous company called Ingenious. It's had 10+ years of development. EyeSight has over 300 customers worldwide. So it's a very mature product. It's a very robust product. So I mentioned that EyeSight is this toolkit for process automation where you can link different codes together. EyeSight, what we call connectors or components connectors, allows those applications to be included in a SimFlow. So these are all of our components that are available with EyeSight. That includes including CAE and CFD codes in that process. It includes CAD codes and incorporating them in this process automation. It includes mathematical codes like Excel, MATLAB, data matching for matching simulation data to test data, general calculator. And then there's also multi-purpose components which allow you to connect pretty much anything. You can connect internal codes, little shell scripts. It's very easy to create new components as well to connect essentially any software to an EyeSight SimFlow. Okay, so let's get back to our problem, the composites optimization of an aircraft winglet. So what we're going to do here is put together a very simple SimFlow, and that SimFlow, which you can see in the top graphic here, is going to include just a couple of components. The first component is a composites database. So as part of this SimFlow, we're going to import the very latest material properties that maybe our test group has tested, and we're going to map those into our simulation model for analysis. Now again, traditionally, this is kind of a tedious process of getting the very latest composite properties from the test group, modifying your model. With this EyeSight SimFlow, whenever the test group updates their composites database, when we run this SimFlow, it automatically grabs that latest version and applies those material properties to our, in this case, Abaqus simulation. So that's the first part, the composites database. We're then going to input that into a data exchanger, which maps those data properties for our Abaqus simulation. And I'll get into the details of some of that in a few slides here. So the objective of our optimization is to obviously survive the loads, and that survivability is based on a SIWO failure index. So we're going to look at ply by ply, element by element, the SIWO failure criteria, and make sure that it's surviving. The other objective is we want to minimize the number of plies. And again, the thought is that minimizing the number of plies is going to minimize our cost and minimize our weight. Our design variables include number of plies, so we can have 2, 3, 4, or 5 plies as part of this composite winglet. And we're also going to vary the ply angles between minus 90 degrees and 90 degrees in 15-degree increments. So all these variables give us, I think, roughly 60,000 different possible designs. Okay. So again, this is the iSight SimFlow for this optimization in a little bit more detail. So we start with Excel as the first part of the SimFlow, and that's our composites material database. We then have an input arrays script, which manipulates that Excel data and resizes the plies and the arrays. We then have a data exchanger, which maps those properties, the new composite properties, into the Abaqus input file. And then we perform our Abaqus simulation, and again, post-processing, looking at that SIWO failure index. So I'm going to talk about each one of these components in just a little bit of detail to give you a bit of a feel for it. So for the Excel component, there's a direct link between iSight and Excel. It allows for parameter mapping, macro execution. You can either do single cell mapping or multiple cell mapping. You can actually, if you have named arrays or named cells in Excel, it'll map those to your properties automatically. So for example, if we had a cell in the Excel and that cell name was composite material, we can give that same parameter name to the Abaqus input deck and it'll create that mapping directly. So in this case, you can see what looks like Excel is actually the iSight component, and the highlighted cells are the parameters and the values that we're going to map into our Abaqus simulation for the optimization. The next component is the data exchanger. The data exchanger is really used to read a file, write a file, can be used for name value parsing if you need to parse some values. You can create for loops, while loops. So it's really just an exchanger of information between two particular codes. And the last component is the Abaqus component. And again, this is a direct link from iSight to Abaqus. It includes modification of the Abaqus input deck or our CAE model file. It includes execution of the Abaqus solver. And this component also includes the extraction of output variables from the .dat, which is a text file, and also the ODB result file, which is our binary output file. So it allows you to map the result sets back to your goals for the optimization. So this is a full look at our iSight SimFlow. So in this view you can see, again, this is a different view, but it's the same SimFlow where we have Excel into the input arrays, data exchanger, and then the Abaqus simulation. But in this case what we're looking at is the parameters or the variables that we're passing from one software code into the next software code. And in iSight it's very easy to change. You can actually click on these links and reassociate a parameter from Excel through the data exchanger into the Abaqus input deck just by changing where these arrows point. So it's very intuitive, very easy to use. So that was a little introduction and overview of the SimFlow, the actual definition of how the parameters are going to map between different software codes. This is a fairly simple SimFlow. We only have 4 components to it. Some of our customers have SimFlows where there are literally 500 different components, and it's really a way to bring multiple groups in your organization together. So that's iSight SimFlows. Let's talk about optimization for a moment, because this SimFlow that we've created, at the very top we have this optimization box. So SimFlow can just be process automation, where it's just going to execute these tasks or this flow once. Or in this case, when we have the optimization folder at the top, it's actually going to do an optimization and loop over these components multiple times. So we have multiple optimization techniques in EyeSight. We have gradient techniques, we have pattern search techniques, and we have exploratory evolutionary techniques. All in all, we have over 20 different optimization techniques. Again, EyeSight is very easy to use, so if you're not sure which technique to use, you can actually choose a technique and it gives you some description of that technique, what kind of problems it's good for, linear problems, nonlinear problems, large variable number of problems, or problems that have small variables. So in this case, for this optimization, I'm going to use the genetic algorithm technique. So these show some of the results of our optimization. So I'm actually going to start at the very bottom here in this graph here. And what we're looking at is the number of designs. So out of our possible, I think it was 60,000 possible designs, it solved 181 different designs. And on the vertical axis, we have our actual SciWu failure criteria. So any design that has a SciWu failure criteria above 1 is a bad design. So this is our 1, so all these designs under 1 is a good design. We can also look at this on a plot of the different number of plies. So in this plot at the top here, we have our different designs, again 181 different designs, and now we can see those designs ranked by the 2-ply designs, the 3-ply designs, the 4-ply designs, or the 5-ply designs. And again, our colors are the same for these dots. So again, down here you can see all the bad designs are red dots, all the good designs, the passing designs, are black dots. So we can see that for our 2-ply design, both of those designs have red dots. So they couldn't find a passing definition with just 2 plies. For our 3-ply designs, we have a lot of red dots, but we also have some black dots, which are passing designs. 4-ply design, again, mostly black dots, but a couple of reds. And then our 5-ply design is all black dots, so those are all survivable designs. The last thing we can do is look at our correlation matrix. So this graph here out of EyeSight shows us the influence that different parameters or variability in different parameters have on our final design. So obviously the ply material and the number of plies has the most effect on whether this is going to be a passing or a not passing design. Okay, so that's a lot of simulation jobs. 181 different designs were evaluated. So that's 181 Abacus simulations. In this case, there were linear analysis simulations. So this actual optimization took 5 hours on my dual-core laptop. But the nice thing about EyeSight is it's set up to handle multiple processors. So we could use parallel processing and reduce this 5-hour runtime down to 30 minutes if we expanded it to 32 CPUs. So yes, optimization takes a long time, but we can take advantage of computer resources to make it a very reasonable amount of wall clock time. Okay, so let's investigate our results a little bit further. So we have optimized results for 2 plies, 3 plies, 4 plies, and 5 plies. So this is another different way to look at the output. This is called a Pareto front output. And we're looking at, on the bottom, our x-axis is our SciWu failure criteria. So again, anything under 1 is a passing design. On the vertical axis, we have our total number of plies. And what we can see is for 2 plies, again, there's 2 plies, there's no designs that were passing. For 3 plies, there's a lot of designs that failed, but we have a couple of passing designs. 4 plies and then 5 plies, all the designs were passing. And you can see the actual results in the bottom table here for the different number of plies, the optimum ply angles, the peak stress, and then we just made some assessment of the cost and the weight based on those number of plies. So again, this Pareto front shows us the very best design for those different number of plies. Another important thing to understand is that, remember, each one of these data points is an actual simulation. So EyeSight links each data point back to the result file back to the model file. So you can directly from a data point click on that and say I want to bring up that model and that result set in this case, Abacus Viewer. So you can get directly from the EyeSight results looking at your contour plot of stress in your post-processing routine. So again, it just makes navigating and understanding some of these results a lot easier. Okay. So which optimized design is the best design? So this is the contour plot of our 4 different designs. Now we have our baseline design, which is our 2-ply design. Again, this had ply angles of 0 degrees and 30 degrees, and its SIWU index was above 1, so this is a failing design. So there's no 2-ply designs that passed our criteria. Next we have our 3-ply design. So our 3-ply design, the optimal design, the design that was on that Pareto front, had ply angles of, it looks like 15 degrees, 15 degrees, and 90 degrees. It had a SIWU index of 0.8, which is passing. So that's a valid passing design. We have a 4-ply design, which had ply angles of 0 degrees, 15, 0, and 90. Its SIWU failure index was 0.4, which is very low. And again, this is a passing design, so that's a valid design. And then we had our 5-ply design. Its ply angles were 90, 90, 15, 15, 90. Again, a SIWU index of 0.3, which is a passing design. So again, we have to ask ourselves, which one of these designs is the best design? So normally, we would say the 3-ply design is the best design. It's the lightest, it passes our failure criteria, it had a SIWU index of 0.8, uses the least amount of material, so we can infer that it's probably the cheapest to build, the cheapest to manufacture. But is it really the best choice? Is just being light the real goal of optimization? So let's continue our optimization and now introduce and look at reliability and robustness. So what we're going to do now is run a Monte Carlo simulation on that optimized 3-ply design. And we're going to introduce variables, real variables that we see in the physical world, the world that we live in. So we're going to introduce a variation in the actual ply angle. So maybe we're not going to be able to lay up that ply exactly at 15 degrees. Maybe it'll be plus minus 10 degrees. So maybe it'll be, when the person physically lays up that ply on the factory floor, maybe it's going to be 13 degrees or 17 degrees. There's going to be some variability in the actual angle of that ply. We're also going to introduce variation in the material properties. So maybe we don't know exactly what our material properties are going to be. So we're going to introduce a variability of plus minus 10%. We're also going to introduce a variation in ply thickness. So again, depending on how we lay this up, depending on how we vacuum bag it, or the temperature, the ambient temperature that day, or the humidity that day, we're going to have some variation in our process of curing, and we're going to account for that by a variation in the actual ply thickness. So we're going to introduce these variabilities, plus or minus 10% on ply angle, plus or minus 10% on material properties, and plus or minus 10% on the ply thickness. And we're doing this through a Monte Carlo simulation. So for each of these variations, we can introduce the distribution. In this case, we're just taking a normal distribution of those factors. Okay, so how does that change our result? So this is the result from the Monte Carlo simulation for the best 3-ply design that we had. So the pink crossbars here show where our initial design was, or optimized, traditionally optimized design. Remember, it passed our SIWU failure index. This red line is a SIWU failure index of 1. Our initial design was at 0.8. And you can see when we introduce these variations, we get a large scattering of performance of this composite winglet. And you also notice that we have multiple designs that now fail. So, if we looked at the statistics, the mean of our designs still has a passing SIWU index of 0.83. Our standard deviation is 0.15, and then we have a minimum and a maximum, and our maximum is above our limit of 1.0. So we have an 87% of probability that our design is going to be less than our critical limit of 1.0. What this means is that we have a 13% probability that our designs is going to fail. Saying that another way, if we make 100 composite winglets using this, quote, optimized 3-ply design, 13 of those winglets are going to fail. So that means that this is a very unreliable design. Let's take a look at our 4-ply design. So again, this is our optimized 4-ply design. It had an initial SIWU failure index of 0.4, which was passing. And again, we can see that with the purple dot and the purple lines there. When we introduced the same amount of variation, so again, the same plus or minus 10% in ply angle, in material properties, and in ply thickness, we now have a mean of 0.45 for the SIWU, a standard deviation of 0.09, which means our minimum SIWU is going to be 0.34 and our maximum is 0.72. So the probability of our design passing that critical limit of 1.0 is 100%. So this Monte Carlo simulation results in a 0% probability that some designs are going to fail. In other words, if we make 100 of these composite winglets using the 4-ply design, 100 of them should pass and should survive in the field. So this means we have a very reliable design. So let's look at this in a little bit different graph. In this case, what we're looking at is the green dots are our 4-ply design, and the red dots are our 3-ply design. And again, these are the results from the Monte Carlo simulations. The vertical axis is the SIWU failure criteria. So again, the red line here at 1 is our critical line. So we need designs that fall underneath that. So again, for the 100 different variations, the variability of our design, for the 4-ply design, all of those green dots fall below the red line. For our 3-ply design, we have multiple designs or multiple products, if we built them, that would fail our critical criteria. So that's the same information as we saw in the previous charts. The other thing we can see in this chart is we can look at the scatter. So just whether the design fails or doesn't fail is a measure of reliability. There's another measure of robustness, which we can see in this plot. So for our 4-ply design, you can see that the scatter in results is from about 0.7 to 0.3, maybe 0.4. For the 3-ply design, you can see that we have a scattering in the results of from about 0.6 to 1.2. So it's about 0.6 of that SIWU failure index of scatter. And this is a measure of robustness. So we have reliability and robustness. Reliability is if it's going to pass. Robustness is what is the scatter. So for the same amount of variation of input, our 3-ply design, it has a lot more scatter. With the same amount of variability in input, our 4-ply design has a lot more consistent performance. It has less scatter. So what does that mean in the field? What does that mean in reality? If we make 100 of these winglets, the performance that the operators are going to see, if it's going to be a drag reduction, increased lift, that performance for the 4-ply design is going to be more consistent. The performance of the 3-ply design, some are going to fail, but also even the ones that don't fail are going to have a large scattering of actual performance. So if we quote an airline that our winglet will save them 3% in fuel efficiency, well, for the 3-ply design, that may be 3% plus or minus 2%. For the 4-ply design, that might be 3% plus or minus 1%. So robustness, reliability, they're a little bit different, and iSight allows us to optimize for both of them and also have insight into both of them. So we perform this as two different sim flows. If you remember before, we started with the optimization sim flow, and we had our multiple tasks with the Excel data exchanger and then the Abacus simulation. But we can do this as one single sim flow, where we can perform the optimization, but also look at robustness and reliability. So in a single sim flow, we can encapsulate the Monte Carlo simulation. So our optimization is going to drive a Monte Carlo simulation, which looks at the variabilities, and that is part of that optimization loop. With iSight, you can have multiple nested loops. So in this case, we just have kind of two loops that are going on. Again, some of our customers have up to, I've seen 20 different nested loops as part of an iSight sim flow. So if we perform this simulation where we have, again, introducing random variables or some variations in the ply angles, the material properties, the ply thicknesses, and then perform our optimization, we'll get the same results that we saw in the previous slide with the scattering of different designs. Okay. So in summary, the real goal of optimization is, or should be, beyond just trying to make a part or component light. The real goal of optimization should focus on robustness, it should focus on reliability, it should take into account variances in input, variables such as the ply angles, the material properties, the loading condition, which we didn't look at this time, but we could have variations in our loading and see how that changes our results as well. The real goal of the optimization should be to come up with a design that's, yes, light, yes, survives the loads, but is also robust, reliable, and will survive in-field operations. iSight is a toolkit, a framework from Simulia that provides utilities for process automation, for optimization, and also for the evaluation of robustness and reliability. And that is my final slide. So thank you all for attending.